Greetings everybody. In this video we are going to explain the MATLAB code for plotting the bifurcation diagram for continuous time systems, using the technique of local maxima. I have another video where I explain a different technique that uses the so-called Poincaré cut. That technique is a bit more technical. The technique that I'm gonna show you in this video that uses the local maxima, it's much easier to implement. It doesn't depend on the specific system at hand. You just need to choose a specific state and that's it. So it's more uniform, I would say, or more universal across different systems. I have another video explaining continuous time bifurcation diagrams using local maxima. I'm gonna put it in the description of the video. So you first see that video, and then come back to see the code. So the code is extremely fast, and very easy. So we start by, first of all, defining our chaotic system. So I have here a function. Now remember, you can do this in a separate file, So you can create a new file, define the function in a separate file and save this file with the same name as your function. I'm using the Rossler system for my simulations. So if I were to save this, I would save this file with the name of Rossler. If you don't want to save this into a separate file, which I'm not gonna do, you can simply define this function. Let me move this a little higher. Let me also increase the text size for you. So you just need to put this function at the end of your script. So either put it in a separate file or at the end of your script. This is a very simple function that tells MATLAB what are the differential equations describing the Rossler system. So the Rossler systems, I always put t here, the time, but we don't use time in the system because it doesn't explicitly have time in the differential equations. So it has the state x and it has three parameters, a, b, and c, because the Rossler system has three different parameters. So this is how we call the function, and the function returns dx. As you can understand, dx is not the default name, you can name it whatever you like, is basically, the vector that defines the differential equations that describe the system. So basically here on dx, I'm gonna put this vector equal to, the differential equations of the system. So basically, the first differential equation of the Rossler system is minus x2 minus x3, So this x parenthesis 2, x parenthesis 3 denotes the state of the Rossler system, So we have minus x2 minus x3. Then change line. So the second differential equation is x1 plus a times x2. So this is the function describing the second differential equation. Basically, we have x2 dot equals this thing. Then change line. And the third differential equation is b times x1 minus c, which is the parameter, and in all of this in a parenthesis times x3. So basically, these are the three differential equations describing the system, You don't have to define the left-hand side of the differential equation, x1 dot, x2 dot, x3 dot, This is understood here. It is understood that dx is basically the vector describing the differential equations, So this is how we define the Rossler system. And note this, a, b, and c are defined on the call of the function because they are parameters. We are going to change their values, Either put this at the end of the script or put this in a different file, and save it with the same name. So now let's go to the code for plotting the bifurcation diagram. By the way, I'm gonna put a link for this code in the description of the video. So let me move this up so you can see everything. Now the first thing you need to do is set up the parameters of the system. So I'm gonna put the bifurcation diagram here and plot it with respect to parameter A, as you see right here. I hope I'm not blocking the view. And so, since A is the parameter that changes, B and C are fixed. So I choose B equals 2, C equals 4. You're gonna ask, Lazarus, how do I choose them? Well, if the system is well known, there will be some paper giving you the values. If the system is new, you need to study them and find out which are the parameters that give chaos. I fix the initial conditions, so x0, which denotes the initial conditions, is 0.1, 0.1, 0.1. So now, let's choose the simulation parameters. To plot a very accurate bifurcation diagram, you need to simulate the system for a long time. Okay, so here I choose 4,500 seconds of simulation. Okay, so T here is the simulation time. And you also remember from the previous video, you need to discard the transient behavior. This is very, very important. Okay, so the transient behavior here, I choose 500 seconds because I have already tested the system. 500 seconds is enough. These are default values. You can change them depending on your own system. Okay, and then I choose the integration step. Okay, dt is 0.01. You can choose a different one. Remember, OD45 that I'm using is a variable step, which means internally it uses a variable step, but when it gives me back the solution of the system, it's gonna give me the solution of the system at specific time intervals defined by dt equals 0.01. Okay, so these are the initial, setup for simulation. Now, to plot the local maxima, we need to choose which state we're going to study. We are going to plot the local maxima of the first, second, or third state, whichever you like. I choose the first state. If you want to choose another state, okay, you're going to get a different graph, but qualitatively, the behavior will be the same. Okay. Then, this is an optional step. I can also choose the parameters for the OD45 that I'm going to choose, that I'm going to call when solving the system. This is optional. You can comment this out. I choose a relative tolerance of 10 to the minus 4. Okay, but this is optional. And then let's set the bifurcation parameter. Now, as you see in the graph right here, I want to study how the system behaves from 0.3 up to 0.45. Okay, so I choose the interval, which is the bifurcation interval, going from 0.3, okay, to 0.45, and then I need to choose the step size. Remember, if you choose a very small step size, the simulation is going to take a lot of time. But the diagram is going to be just like the one you see here, which is very well detailed. If you want to choose a bigger epsilon right here, the bifurcation diagram is going to look a bit more crude. Okay, it's going to look less detailed. And you can choose whatever you like. Okay. Now, this is the setup for the bifurcation parameter. And now what I do, which helps a lot with the simulation, is pre-save an empty matrix, which is M. This matrix M is the matrix in which I'm going to save the local maxima values. Okay, and I pre-save it by including 3000 rows. Okay, again, this is just a default value. You can make it larger if you like, 4000, just to be sure that it works properly. And the number of columns is equal to the length of this bifurcation vector that we have created. Okay, it's the length of the step interval. If you don't pre-save that, you can still write the code. This is my suggestion. You can do very easily a variation that doesn't require that. Okay, but be sure to make the rows longer than the amount of local maxima you're gonna get. Okay, otherwise you may end up filling this matrix by default. MATLAB will do it. It will fill this matrix with zeros. Okay, because this is what MATLAB does when it appends values to a matrix. Okay, no worry about that. 3000 is more than enough. If you don't like that, use 4000. Okay, so now let's begin. This is just a dummy variable, pos from position. So to plot the bifurcation diagram, we simply have a for loop. For a, which is the bifurcation parameter, equals to the step interval. Remember, step interval is 0.3 up to 0.45 with this very small step. Okay, so let's see what the code does. Let me increase the text a little bit, which is going to be easier for you to read. Come on, come on, come on. All right. So we start with alpha, okay, in this step interval. I simply choose to print the value because by printing the value, I can simply observe how quickly the diagram and the algorithm progresses. Okay. This is a dummy variable that uses to index and save the values. So I increase it by 1. It starts from 0 and then it goes plus 1, plus 1, plus 1. Okay. And then what do? We simulate the system by calling it. So I call ODE45, which is the default solver in MATLAB. Okay, variable step solver, very, very good and very efficient. So this is the code. You're going to copy paste it in your own file. ODE45 at t, x, the Rossler system with parameters, I'm sorry, t, x, a, b, and c. Okay, 3 parameters. Of course, B and C are already pre-saved and are fixed, but in each iteration of the for loop, A changes. Okay, so I'm calling this ODE45 for what time? 0 up to 4,500 seconds with a DT step that I have chosen, which is 0.01. Okay, and for initial conditions x0, and for the options, which is the relative tolerance I have right here, 10 to the minus 4. Okay, so this is the code. After I run this code, the system, MATLAB, will solve the Rossler system for this specific time, okay, for these specific parameter values, and for this specific initial condition. And it will return to me, okay, the value of x, which is basically three different states, and t is the variable of time. Okay, then what do? Remember, I need to find the local maxima for the first state. But first, I also need to discard the transient behavior. So this is very easy to do. I do basically using vector indexing, which is a very clever way to do stuff in MATLAB. This index denotes the time that is longer than the transient. So basically, I get t larger than tran. This comparison will return a vector that is the same size as t, but it will include zeros on time that is not slower, sorry, on the time that is lower than the transient, and ones on the time that is higher than the transient. And I use this indexing, this is classic vector indexing in MATLAB, to save the states of the system, okay, after the transient behavior. So first of all, what I do is this. I calculate which position in my solution corresponds to time that is longer than the transient, okay? And then I save this specific part of the vector that corresponds to the solution after the transient, okay, into a separate variable. This is easier for me because I can understand it this way. So X capital, okay, it's the solution of the system for time after the transient, okay, after the first 500 seconds. And then I simply continue by finding the local maxima for the state that I have chosen. Okay, the state index is IDX, which is the state index. I have chosen the first state here. So then on this p variable, I use the built-in function from MATLAB, which is find peaks, which finds the local maxima. Okay, find the local maxima for x capital, but remember x capital includes all the three states, x1, x2, and x3. I need to find the local maxima just for the state of my choice. So the state of my choice is the one given by the index STIDX, and I have chosen the first state. Okay, so this function does exactly that. It finds the peaks, the local maxima, for the first state, okay, after the transient behavior, because we have x capital, okay? So we discard the transient, okay, and then we find the local peaks for the first state. These are all saved in a vector P. And then remember, M is the big matrix where I'm gonna save, all of the local maxima. And then I simply save in a specific column or row here. Yes, in a specific column, which is indicated by POS, which is the position index. Okay, let me zoom out. So POS is the position index. And I go into this specific column and I save the local maxima that I have found. Okay, and that's it. The loop ends and then it continues to the next value of A, and it does it again, solves the system again, discards the transient again, finds the local maxima again, and again, and again, and again, and again, until we run out on the complete bifurcation interval. Okay. Basically, you can do a couple of improvements here to make the code run even faster. Okay, so you can do improvements, but I keep it very simple so that everybody can understand it. Okay, but we can make improvements to make the code run faster. If you can do it yourselves. Okay, and after I complete all of this simulation, I have basically a matrix M, and in this matrix, I have saved all of the local maxima for all of the different parameters that I have saved and simulated the system. Okay. By the way, if you want to run a continuation diagram, at the end of its simulation, what do? You redefine x0 and set it as the final value of x. Okay, x end here means take the final value of your simulation and save it into the x0. If you do that, as the loop progresses again and again and again, the initial condition each time will be the final value from the previous simulation. And this is called continuation diagram. I'm not going to do that here though. I have a classic bifurcation diagram. After the simulation finishes, I have a simple plot command, define a new diagram, and plot the step interval that I have and the matrix M that we have created, and plot them as individual dots with a marker size of 2. And the result looks something like this. And this is the classic bifurcation diagram for the Rossler system. Okay, remember, if you want to choose a smaller step, it will take a bit more time, but it will be much more detailed. Okay, so here, for example, if I zoom in a little bit, I can see a little detail, but you see that since I moved in, it starts to become more crude, you know, it's much less detailed. So if you want to obtain more details in a very small interval, you need to you need to reduce the step size for the bifurcation interval. Okay, but in the default case, the diagram looks amazing. Okay, so I'm gonna put a link into the description of the video for another video explaining the bifurcation diagram in detail. And I'm gonna put a link also for the MATLAB code, this one that I showed you, where you can download it and plot the bifurcation diagram. And the MATLAB code that I'm gonna show you also includes a density-colored bifurcation diagram, which is explained in another video that I'm also going to put in the description of the video. Okay, so we're gonna have a lot of information about bifurcation diagrams. So if you have any questions about the code, write them down in the comments. Okay, and I'll see you in the next video. Thank you very much.